Assalamualaikum warahmatullahi wabarakatuh and good morning to everyone. Today we're going to start our parallel programming subject lecture number 4 in an e-learning mode where I will record lecture videos for myself and I will upload it to the Spectrum. So for this week lectures, it's going to be e-learning mode and also tutorial on Thursday, also going to be in learning mode. So lecture 4 is all about process and threads and some introduction to the programming using Java and C. Okay, we will start our lectures now. Okay, process. Process in a general terms. Okay, process in a general term means execution of data and instruction. So a process is a program in execution. A process is more than a program code, which is sometimes known as a text section. So an instance of the computer program in execution. So process often defined as a program in execution. Okay. Program by itself is not a process. Program is a kind of a passive entity. So such as a file containing a list of instructions stored on disk or called executable file. So there are mostly two common techniques for you to execute the files. Either by double click, you see there is a one, as you can see, some of the software you can double click to running the executable file, or you can also execute a file by a command line. Like you put if you have a programming language C, and then you have output.out, you can just call the command line, or you just type the command line output.out, so that file will be executed, and this is what we call a execution instance of program in execution. So process is a program that is currently being executed on one of the operating system virtual processor. So to execute a program, an operating system creates a number of virtual processors, each of which runs a different program. You can have a word processor, you can have a web server, you can also your media player. So this is what we call a program, and they can have a processor that belongs to each programs. So what is a process table? Process table is created in order to keep track of these virtual processors. The operating system has a process table which containing entries to source CPU register values, memory maps, open files, accounting information, privilege, and so on. So, in a nutshell, we have this process. This is a process, and then you have this one, and you have a pointer here, then you have a process state. So process state is like read, write, create, destroy, and stuff. And then you have a process number. And then you have a program counter. And then you have a registers. Then you have a memory. And then you have an open file. And then you have accounting and data. So this is the process, we call that a PCB, a process control block. So the pointer is a stack pointer. Pointer is a stack pointer. Process state store the respective state of a process. A process number is a unique ID signed to the process. A program counter. So you have a program counter to execute the current process and also for the next process as well. And then you have a memory. You have a memory management system. So you allocate an address in the memory. And then you have an open file list. Information includes the list of files. And then you have an accounting. You have an accounting and data, where the field includes information about the amount of CPU use, time constraint, jobs or process number. So this keep the accounting such as amount of CPUs, amount of CPU use, time constraint, jobs or process number, and etc. So this is basically a process control block. What is a process? What is a process contains? A pointer, a process state, process number, program counter, registers, memory, open file list, accounting, and data. So each program gets executed on a virtual processor. Multiple processors may be concurrently sharing the same CPU and other hardware resources. So process also can have you can also have like a process 1. This is a process 2. This process 1, let's say this is the web server, and this is a process 2, which is like a database or something, and sharing the same CPU and other hardware resources, and then they share the same CPU and also like memory and stuff. And they also can have a multiple CPU here, such as in a parallel programming, or they want to do it in a parallel process. So a process consists of execution environment together with one or more threads. So threads, we will learn after this. What's a threads? So execution environment. So just assume this as an icon. Execution environment, just assume as an icon of an executable file, or you can call this executable file by a command line, or you run something from your code. So an execution environment primarily consists of an address space, a thread synchronization and communication resources such as semaphores, and communication interface. Okay, what is semaphores? Semaphores is, okay, for the semaphores, semaphores is, you can have semaphores exist in C or Java. It's basically, if you want to imagine semaphore is like a bouncer for a nightclub. This is one of the examples that is widely used. Semaphore is like a bouncer in a nightclub. It has a certain capacity enforced by a bouncer. One, it is okay. You have a nightclub, or you can use any other system, but it's easier for me to use the nightclub. You have a nightclub here, and you have a bouncer here. So like nightclub, maybe they can have at most, they can fill about 200 people at one time. That is a maximum capacity. So what bouncer do is, once the nightclub is full, the bouncer will stop people from coming. So people will queue outside. So this is the bouncer. So people will queue outside. So once this is full, so people cannot come in. So the bouncer will restricted or block all this. This is semaphore. We block all these people from coming into the club. So when one person leave, there is, let's say, one person leave, and this one, the first in the queue, will go in. If you take the first in first out concept, so one person enters from the head of the queue. So basically there are two arguments for semaphores. Semaphore, you have a total club capacity, you have a total capacity, and the current available places. Total capacity and a current available places. So this is semaphores. Just like a bouncer that limit the number of people going to the nightclubs, and if one people leave, the bouncer will allow one people to move in. And the communication interference, for example, socket. So this is a communication between a process. High level resources such as open files and windows. Execution environments are normally expensive to create and manage, but several threads can share them, and that is, they can share all resources accessible with them. And then you have an address space, a unit of management. A unit of management of a process virtual memories. Just assume this as okay. You have you have a table here. You have a process ID. You have a process ID, and also you have a PCB, process control block, and then this is process 1, process 2, process 3, and then you have a memory allocation here. This is a memory address. So how does this okay, let's say PCB, and then how do you allocate which process to the which memory allocated address? So this is a memory allocation. Unit of management of process virtual memory address space. So you have here, this is process ID 1, process ID 2, and so on until process ID n. So cost of process and processing, concurrency, transparency. Address space. Each time a process is created, the operating system must create a complete independent address space. So this is the address space. You have like 1000, 2000, like 7000. This is what we call an address space. Allocation, initializing memory segments by, for example, zeroing a data segment, copying the associated program into text segment, and setting up a stack for temporary data. So stack is like a local function variables that are automatically created. So switching the CPU between two processes, you can have that as well. Modify registers of the memory management unit, MMU. The operating system has to modify registers of the memory management unit, MMU, and invalidate address translation caches such as the translation locus site buffer, TLB. So this is all the process. And then you have to swap process between main memory and disk. If the operating system supports more processes that it can simultaneously hold in main memory, it may have to swap processes between main memory and disk before the actual switch can take place. Remember the diagram. If you have remember the von Neumann diagram. So you have a RAM here. This is CPU and ALU. This is the RAM, and this is the disk. So what we say that swap process between main memory and disk. If the operating system supports more process that it can simultaneously hold in main memory, it may have to swap process. Okay, it will be faster if you refer to main memory, which is RAM. And let's say this RAM are full. Let's say this is full. So the CPU have to allocate, have to call something in a disk, which will be much slower. If the RAM allocation process in the RAM, process in the main memory full, the CPU has to call the process from the swap process between main memory and disk before the actual switch can take place. So you have to switch from RAM. Let's say RAM is full, so CPU have to allocate or call from a disk, which is much more smaller. So this is what we call a cost of process and processing. So which is expensive and creates more bottleneck and complication. So this is like the application service, a middleware, and you have a OS, operating system, which consists of kernel, libraries, and servers. And then you have a node 1. Let's say you have multiple machine. You have OS 1, computer and network hardware. And then you have a OS 2, process, threads, and communication, and computer and network hardware. This is node 2. So use the same middleware and application service based on the protocol. So kernels, if you learn operating system, kernels is the heart of the operating system. Kernels and server processes are the components that manage resources and presents client with an interface to the resources. A combination of libraries, kernels, and servers may be called upon to perform the following invocation-related tasks: communication and scheduling. Okay? Communication and scheduling. So you have here kernel, and you have a task management. What does kernel do? Task management, synchronization and communication, memory management, timer management, interrupt and event handling, and device input-output management. So communication is between the process. Communication can between the between different process. Between different process or nodes, etc. And scheduling, like you want to see process 1, process 2, process 3, and so on, scheduled in a sequential way. And this is handled on one core, and you have more you can handle, like core 1, and this is core 2. So you can handle in a parallel programming way. So this is schedule. You go for P1. This should be a P1, P2, and this should be a P3. So P1 goes first, and then P2, and then P3. So the same as this as well. P1, P2, and this one is P3. So this is scheduling. Time, mostly in a time unit. So the core OS components and their responsibility are process manager, creation of and operation upon a process. A thread manager, thread creation, synchronization and scheduling. And communication manager. With communication between threads attached to different processes on the same computer. Some kernels also support communications between threads in remote processes. Other kernels have no notion of other computers built into them, and additional service is required for external communication. So, okay, thread is a unit, a smaller unit of process. If you talk about thread, okay, let's say you have a P1 here. you have a process number 1, and then you have a memory and resources, and then you have thread. This is we call a thread 1, responding to the process 1, thread 1, and then you have a thread 2 corresponding to process 1, and then you have a thread 3 corresponding to. So you can call this application or programs a web server. When you execute, become a process, and this process can be divided between different threads. Okay, you have thread number 1, thread 2, and thread 3. This is a process. Process 1, this P process, T is the thread, and this is the memory and resources. Sorry for my handwriting. Memory and resources. Any resources like files and others. And then you have a process 2. Process 2, this is the process. And then this is the memory and resources. And then this is a thread. Let's say this is thread corresponding to process 2, thread 1, thread 2, and this one, thread 3 corresponding to thread 2. So this is, let's say this is a database. So in a multi-processing environment, each process executes the same code but has its own memory and file resources. And threads is a smaller unit of process. A process can have 1 or 1,000 threads, doesn't matter. So this is a thread. This is a thread. Thread is a unit of process. Smaller unit of process. And then you have a memory manager, management of physical and virtual memory, and supervisors. This is all your OS, okay? OS do the process manager, thread manager, communication manager, memory manager, and a supervisor. Dispatching of interrupts, system calls, traps, and other exceptions. It also control of memory management unit and hardware caches, processors and floating point unit registers manipulation. This is also known as the hardware abstraction layer in Windows. So this all is a responsibility of OS or kernel in OS. So now you have a process manager, and you have a communication manager, thread manager, memory manager, and supervisor. So this is a OS functionality. So a thread is operating system abstraction of an activity. Operating system abstraction of an activity. So this is the process, the whole block. This is a process. Sorry for the handwriting. This is the process. And then you have a thread 1, thread 2, and thread 3. And this is the process, you have thread 1, thread 2, and thread 3. So thread is execute its own piece of code independently from other threads. So thread 1 is independent of thread 2. Thread 1 independent of thread 2, and so on. So if thread 1 if thread 1 meaning that thread 2 doesn't depends on the thread 1, meaning that if thread 1 execute, thread 2 can also execute without having to wait for thread 1 to finish executing first. So threads can be created and destroyed dynamically as needed. You can create and you can also destroy the thread dynamically. The central aim of having multiple threads of execution is to maximize the degree of concurrent execution between operations, thus enabling the overlap of computation with input and output, and enabling concurrent processing on the multiprocessors. So this can be particularly helpful within servers where concurrent processes of client requests can reduce the tendency for servers to become bottlenecks. For example, one thread can process a client request while a second thread servicing another request waits for this access to complete. So you have a concurrent process or multiple process. So with the thread you can solve a server's bottleneck. So one thread can process a client request, and while second thread servicing another request wait for this access to complete. So this thread can can make more work as efficient as possible because it divide the task the process between different thread or task. So many older operating system allow only one thread per process. But this is the old operating system. Now, like a process, a thread executes its own piece of code different from other threads. So now operating system can also allow multiple threads per process. In contrast to process, no attempt is made to achieve a high degree of concurrency transparency if this would result in performance degradation. So it doesn't have to be transparent. The thread doesn't have to be transparent as compared to process because this will result in performance degradation. Therefore, a thread system generally maintains only the minimum information to allow a CPU to be shared by several threads. In particular, a thread context often consists of nothing more than the CPU context, along with some other information, thread management. So only a minimum information, and it doesn't make transparency to the OS because because this is only a lightweight process. It's only a lightweight process, and you want to do works more faster and more efficiently. For example, a thread system may be keep track of the fact that a thread is currently blocked on a mutex variable so as not to select it for execution. So we call it a mutex. Mutex is actually a simple locking mechanism. Mutex is a simple locking mechanism to implement a critical section. Let's say if a given resources in your application needs to be utilized by at most one thread at any time. So mutex or lock can be implemented for thread safe operation on a shared resources. So you have a mutex is actually a lock because if you have a critical session that maybe only one thread can run at any time, so you can use a mutex lock. This actually happens in the shared resources. Information that is not strictly necessary to manage multiple threads is generally ignored. For this reason, protecting data against inappropriate access by threads within a single process is left entirely to application developers, not OS. Okay. So if two applications are run on a computer, let's say you have a Microsoft Word and you have a Microsoft Access. Two processes are created. Multitasking of two or more processes is known as process-based multitasking. Multitasking of two or more threads is known as thread-based multitasking. This is what I call a multi-threading. Okay, a multi-threading. The concept of multi-threading in a programming language refers to thread-based multitasking. So process-based multi is totally controlled by the operating system. Okay, you have the operating system control the process, but thread-based can be controlled by the programmer to some extent in a program. So let's say you have this one is the Microsoft Word, this is the Microsoft Office Word, and this is the Microsoft Access. So the process 1 and process 2 controlled by OS. The whole process here The whole process here is controlled by OS. But the thread is controlled by, as it say here, thread-based multitasking can be controlled by the programmer to some extent in a program. So this is controlled by the programmer or the code. How the programmer code the way, how do the programmer code for multi-threading? So the programmer must create his or her code efficiently in order for thread to run in a smooth way. So you have a single thread process. As I mentioned before, process can be one thread, or process can have a multiple threaded 1000 thread whatsoever. So it is a single instruction stream if one thread. For multiple threaded is a multiple instruction stream. So thread is a smaller unit of process. You can divide a process with a number of thread. So what is the difference between a process and a thread? You have here a process is typically independent, has considerably more state information than thread, much more expensive to implement. Separate address spaces. So you have a process one. If you have a memory here, this is process one allocated a memory, let's say 2000. Process 2 allocated a memory 3000. This is the main memory, and process 3 allocated at, let's say, 5000. So this is the separate address space. Link interact only through system IPC, inter-process communication. So this is a process, interact only through system IPC. Process 1 process 1 want to communicate with process 2, process 2 want to communicate with this is only by IPC, inter-process communication. So what is thread? Thread is here, subsets of process, smaller unit of process, multiple thread within a process, share process state memory. So whatever, okay, you have a process here, this is a thread, multiple thread within process, share process state memory and stuff. So whatever, like the memory, the state and everything from for thread is shared by its concurrent process or respective process. So thread share the resource memory based on the process that it belongs to. Thread share the address space. So thread is based on the address space. Thread address space is based on the process address base. Threads are cheaper to create and manage than processes, and resource sharing can be achieved more efficiently between threads than between processes because threads share an execution environment. So when you have a smaller unit, it is more cheaper to create and to manage. And so you have a sharing resources also more, you can share resources more efficiently between threads. So we go for the thread implementation. So threads are often provided in the form of thread package. We will learn in the programming. A thread package contains operation to create or destroy threads as well as operation on synchronization variables such as mutexes and condition variables. As I said, mutex is a locking mechanism in critical for a critical process or thread. Two approaches to implement a thread package. One is to construct a thread library that is executed entirely in a user mode or user mode thread, and to have a kernel be aware of threads and schedule them, or kernel mode thread. So what is the user mode thread? So user mode thread, okay, if you go to the user level thread, we call it user level thread. So you have a user level thread, you have a process 1, and then you have a multiple thread here, process 2, you have a multiple, and then you have a TL, or thread. TL is a thread, thread library. So you have here a user space. This is a user space. So kernel thread management is not aware of say, okay, this is a user space, and then this is the kernel space. So even though you have here multiple threads, but the kernel will manage them. Kernel will manage them if they were single threaded process, like they are single threaded scheme. Okay, and then you go to the CPU. So all the creation and destroying of thread happens here in the user space. So user create and also destroy the thread operation. All are done in here, user space. Creation and destroying. Creation and destroying of thread happens here. So the kernel the kernel doesn't know what happens in the user space. Whatever thread, multiple threads here, the kernel will manage them like they are single thread scheme, and this will process to the CPU. So what is the advantage for first approach? First is cheap to create and destroy threads because it is done on the user space only. So it is cheap to create and destroy threads. Because all thread administration is kept in the user's address space, the price of creating a thread is primarily determined by the cost for allocating memory to set up a thread stack. So as we mentioned before, stack is local function variables that are automatically allocated in the memory. So analogously, destroying a thread mainly involves freeing memory for the stack, which is no longer used. So you can say that if the memory, this thread already completed, the task of completing this thread is already done. So you just free the memory. So this is how you destroy a thread. And both operations are cheap. Okay? Both operations are cheap because it is faster to create. Okay. Both operations are cheap. Well, this is which is now both operations. Actually, user mode is more cheap. Is a cheaper. So you don't have a kernel permission and faster to create and manage a thread. And also the first approach you can run in any OS, Windows, Unix, Macintosh. You can run it on any other OS. So switching thread context can often be done in just a few instructions. Only the values of CPU registers need to be stored and subsequently reloaded with the previously stored values of the thread to which it being switched. This is all the memory management. The value of CPU register need to be stored and subsequently reloaded with the previous stored values of the thread to which is being switched. There is no need to change memory maps, flush the translation look-aside buffer, TLB, do CPU canting, and so on. Switching thread context is done when two threads need to synchronize. For example, when entering a section of shared data. So this is all the advantage of the user level thread. But there is also a disadvantage using the user level thread. First is invocation of a blocking system call will immediately block the entire process to which the thread belongs, and thus all other threads in that process. Let's say you have a thread 1, thread 2, and thread 3, and this is the process. So if this one is blocked, thread 2 and thread T cannot be run anymore. You have to wait until T1 is unblocked to run thread number 2 and thread number 3. So one thread block, the system call will immediately block the entire process. If T1 are blocked, T2, T3 also will be blocked to which the thread belongs, and that's all other threads in that process. If you have 1,000 threads, that 1,000 threads will be blocked as well. There is a lack of coordination between threads and operating system kernel. Therefore, process as whole gets one-time slice irrespective of whether the process has one thread or 1,000 threads within. It's up to each thread to relinquish control to other threads. So as I said, this one you have a multiple threads, maybe 1,000 threads in that process or single process. But when it's come to kernel, when it comes to the kernel space from the operating system, it will only treat it as a single thread scheme or one-time slice. We call that one-time slice. And user level thread requires non-blocking system call multi-threaded kernel. Otherwise, the entire process is blocked if one user level thread performs blocking operation, even if there are runnable threads left in the processes. For example, if one thread causes a page fault, then the process will be blocked. So page fault is the memory allocation scheme, first in, first out, least frequently used, and so on, least recently used, and all other schemes. So one thread page fault, the other process, even though it is running, it will be blocked as well. So this is a major drawback of the user level threads. So second approach is by using the kernel space from the OS. Implementing threads in the operating system kernels, every thread operation, creation, deletion, and synchronization will have to be carried out by the kernel, requiring a system call. And also a high price to pay. Okay, it is much more complicated. Switching thread context may now become as expensive as switching process context. As a result, most of the performance benefit of using thread instead of processes then disappears. So it defeats the purpose of thread because the switching process context is much more expensive for process. So if the thread becomes exactly as process, it defeats the purpose of the thread. But one advantage is it can simultaneously schedule multiple threads from the same process on multiple process. So multiple threads is so one of the advantage is multiple threads is treated as a multiple threads from the same process on multiple processes. If the one thread is blocked, okay, one of the great advantage of the kernel user space, kernel user thread, is if one thread is blocked, kernel can show another thread of the same process. Okay, what we have here is, okay, let's say we have this is a process, and you have a thread 1, thread 2, and thread 3. If thread 1 are blocked, if thread 1 is blocked, thread 2 and thread 3 can is still running or can be scheduled to run within the same process. So one of the disadvantages as well, okay, is expensive. So you have to create and destroy thread in kernel OS. So it is much slower if you have to create and destroy thread in the kernel OS or kernel space. So a mode switch to kernel mode is required to transfer control from one thread to another in a process. You have to do a mode switch to kernel mode in order to transfer control from one thread to another in a process. So one of the way you want to implement, you want to combine both the pro of both approach, the user level thread and the kernel level thread, is by combining them together in a thread implementation, or we call it a hybrid approach. And this has specific terms called a lightweight process, or LWP. And LWP run in context of a single heavyweight process, and there can be several LWPs per process, like a multiple threads per process, or several threads per process. The system offers a user level thread package, offering application the user operation for creating and destroying threads. So creating and destroying threads are done in the user level, user space, or we call it a user space, and this is a kernel space. User space, this is the user space, and this is the kernel space. So the package provides facilities for thread synchronization, such as mutexes and condition variables. If I say mutex, the locking variables for the critical application that maybe can allow only one thread per. They can only allow most one thread at any time. So mutex block mutual execution is or we call that mutex is the short form of mutual execution, is a single locking mechanism. Single locking mechanism. The important issue is that the thread package is implemented entirely in user space. In other words, all operations on threads are carried out without intervention of a kernel. So you done all your work in user space. It's much more faster, cheaper, and much more easier to implement or to create or destroying a thread in user space. Kernel space is much more expensive if you want to implement a thread here. The thread package can be shared by multiple lightweight processors. Each LWP can be running its own user level thread. Multi-threaded applications are constructed by creating threads and subsequently assigning each thread to an LWP. Assigning a thread to an LWP is normally implicit and hidden from the programmer. So programmer doesn't need to know about this. Assigning a thread to a lightweight process. So the thread package has a single routine to schedule the next thread. When creating an LWP, which is done by means of system call, the LWP is given its own stack, a local function variables that are automatically allocated, and is instructed to execute the scheduling routine in search of a thread to execute. So they go for the scheduling routine and find which thread has been scheduled to execute. So the thread table, which is used to keep track of the current set of threads, is thus shared by the lightweight processors. Protecting this table to guarantee mutually exclusive access is done by means of mutex and implemented entirely in user space. Synchronization between lightweight process does not require any kernel support. And when an finds a runnable thread, it switches contact to that thread. Meanwhile, other elements may be looking for another runnable thread as well. If threads need to block on a mutex or condition variables, it does the necessary administration and eventually call the scheduling routine. When another runnable thread has been found, the context switch is implemented completely in user space and appears to the LWP as a normal program code. So this is introduction to the threads programming. Threads programming is concurrent programming. You have a thread 1, you have a process, and you have a thread 1, thread 2, thread 3 in a concurrent way. The C threads package is known as PTH. So if you have include PTH path PTH thread dot h or something, yes, in C dot h. So this include PTH has been widely adopted by the standard IEEE. So this is a Java constructor of a management method. So thread group, runnable target, string name, creates a new thread in a suspended state, which will belong to a group and be entered as name. The thread will execute the run method of target. So you have a set priority, in new priority, get priority, sets and return the thread priority, run, executes, start. So initial state is suspended and will take, if you call the start function, it will call to the runnable state. Sleep or long millisecond cause the thread to enter suspended state for a specified time. Yield cause the thread to enter the ready state and invoke the scheduler and destroy the threads. So you have this so this is basically the same thing. Sorry for that. So thread synchronization, thread joins function, long millisecond, blocks the calling thread for up to specified time or until thread has terminated. Thread interrupt threads cause a return from blocking method calls such as sleep, cause it to return from a blocking method call such as sleep. Object wait blocks the calling thread until a call made to notify or notify all, and object waits the thread and the thread is interrupted or specified time has elapsed. And object.notify all function waits respective one or all of any threads that have called wait on objects. So we go for the inter-process communications, IPC. Inter-process communications. So it is independent, not affected by the execution of other processes. The process cooperate with each other. So you have a process A, you have this one, process 1, and you have a thread, and you have a thread library. This is process 2, and then you have a thread, and then this is a thread library. So how do you communicate between process 1 and process 2? You use the IPC. Not affected by the execution of other processes. So process 1 is independent of process 2. You can execute whatever process here and you can execute whatever process 2. But when it's time to communicate, it will use the inter-process communication. It's also a cooperative. The process cooperate with each other. Can affect or be affected by other processes, including sharing data. So some of the process share the same data or resources. So the IPC is the way processes communicate with each other. IPC is a mechanism to transfer data between processes. It allows the process communicate to each other and synchronize their action. So this is inter-process communication. Why is IPC is needed? Of course, to communicate between each process. Not all processes can be easily built in a single process. So in some applications, some procedures, you must have a different process to implement it. So that's why you need IPC. Benefits of IPC is information sharing will be there from one process to another process. Suppose maybe present in our system or other system, in your system or other system. They will communicate with the help of IPC within or between system. You have a resource sharing process, maybe share memory or share data or whatever resource sharing. They can use IPC to communicate with each other. Computation speed up. If you limited resources, those resources can be shared through other and increase the speed or computation. Or synchronization, synchronizing information among process and provides modularity. What is a modularity? Modularity is the you have a different segment in order to have all these segments are combined to create a process. So this is a modularity and also a convenience. So okay, this is the process way of work. Private, so each process has a private address space. So private address space of process A, private address space of process B. No process can write to another process space. And how can we get data from process A to process B? By using the IPC. IPC mechanism, process communicate with each other using two ways, shared memory and message passing. So shared memory, process share the same segment of memory directly. Memory is persistent beyond the lifetime of creating or modifying processes until deleted. So memory, as long as the memory is there, the power is up. So it's persistent beyond lifetime. The memory will still be there, the shared segment. And mutual exclusion must be provided by the person using the shared memory. So process requests a segment, OS maintains the segment. This is the OS address space. OS will maintain the shared segment, and process can attach or detach the segment. It's up to the process. So shared memory, continue. Okay, you have a processor generate information about certain resources and keeps it as a record in the shared memory. And when process B needs to use some resources, data, information from A, it checks the record in the shared memory and use that information. So this is a shared memory. If you use for a shared message passing, let's say process A will call a kernel in order to communicate with process B. So kernel, okay, the first processor will call a kernel, and kernel will call a process B in order for process A and process B to communicate. So kernel become the center, and process A, if you want to communicate process B, first it will call kernel to communicate with process B, and this is one, and if two is kernel call the process B. So this is message passing. It's no use of shared memory if two processes want to communicate. Establish a communication link, not establish a communication link. Start exchanging message using basic primitive like send function, which have message and destination variables, and receive, which have message and host variables. It can be direct or indirect, symmetric or asymmetric, mailbox like a mailbox or ports, symmetric or asymmetric, blocking, unblocking, send blocking, unblocking, receive, and automatic or exclusive buffering. Zero, like zero meaning that no space, bounded, limited space, and unbounded. Unbounded has no limited space, infinity capacity buffers. So zero meaning that no space, bounded mean have a limited space, and unbounded is like no limits of the capacities or no limits in terms of space. So let's say you have a process one sending process, then go to the message passing module, and it will process the ID and message, and then the message passing module will pass to the P2, a receiving process. So what is IPC method? File used to store the resources or information. Those resources will be saved and read after the completion of the program. Signal used in Unix operating system, passing a signal to a processor or interrupting a process. Socket provides point-to-point communication and two-way communication between two processes. So socket is actually a link, call it a socket. Message queue, it provides synchronized and communication protocol. Message placed on the queue, the receiver or sender retrieve the message from the queue, and no need for sender or receiver to interact at the same time. So like if the message queue, like the message queue is only to queue the message, just to provide synchronization and communication protocol. So no need for sender and receiver to interact at the same time. So there's no real-time communication. Just that it happens in a computer, it happens in a very fast, very quick way, and basically you as a user will not realize this one. And a pipe access the output of each process using the standard output, and each process feeds directly as input or standard input. So you have a process, you the output will be a standard output using a pipe A, and will be input to the CPU. And if a CPU wants to send input to the process, it will first produce an output, standard output, going to pipe B, and when going to the process, it will go as a standard input. So this is a communication distributed system. This is basically a OSI 7 layers. This stack, what we call it, application, presentation, session, transport network, data link, physical, this OSI 7 layers. And you have bits that actually appear on the network. So data link layer, network layer. So this is a bits. Message come in bits, okay? And each one has this header, that data link layer header, network layer header, transport layer header, and so on. So this message is bits. Imagine this is like an envelope you have. Imagine this is the envelope that you have, and you have to put all the address, the stamp, and everything. So type of communication distributed system is message-oriented communication, stream-oriented communication, stream synchronization, and multicast communication. So there is a Java thread. Threads are objects in Java language. They can be created by using two different mechanisms. Create a class that extend the standard thread class. Create a class that implement the standard runnable interface. So you can create a class basically the thread class and override the run method. So this is the way you have you define a class, my thread extend thread, and then you create a body, create a thread object, and start execution of created thread. So this is you can do this later in your program using Java or whichever language that you prefer. A simple program created invoking a thread object by extending a standard thread class. So you have you define a class, and then you make this a public void, and then this thread is running, and then you class thread, you define another class, and you have a public static, you define main, and then you call it a my thread function, and you call a start process. So this is that. Create a class, implement interface runnable, and override run. Create a class that extends the standard thread process. So you can override a run where you creating a thread object, thread new thread, thread object, and you override a run method. So a Java program with multiple threads. To illustrate creation of multiple threads in a program performing concurrent operation, let us consider processing of the following mathematical equation. So we have a P is equal to sin x plus cos y plus tangent of z. As these trigonometric functions are independent operations without any dependency between them, they can be executed concurrently. So the sin, cos, and tan is independent of each other. You can run it concurrently together in a parallel way. So this is a mathematical thread. Start, you have mathematical sin, cos, and mathematical operation of sin, cosine, and a tangent. So this is a math thread. So this is a Java program with a multiple threads. After that, the real results can be combined to produce the final results. So thread priority, there are many threads, but some are more important than others. So this is why you have a thread priority. All the thread instances developed have the same priority. The process will schedule fairly without worrying about the order. It is important for different threads to have different priorities. Important threads should always have higher priority than less important ones, while threads that need to run quickly as demand may only need the lowest priority. Example, the garbage collected thread just needs the lowest priority to execute, which means it will not be executed before all other threads are scheduled to run. So the thread classes in Java provide three constant values for priority. So minimum priority is 1, normal priority is 5, and maximum priority is 10. So maximum priority will be given the preference first. So there's also a thread method sleep function cause the current thread to sleep for a specific amount of time in millisecond. Public static void sleep long millisecond through interaction. For example, the code below puts the thread in sleep after in a sleep state for 3 minutes. So you have a 3 slept. So you have a 3 times 60 times 1000. So this is a 3 minutes times 60 seconds. This is a 3 milliseconds times 60 times the 1000. So you want to convert it to the minutes. So is a yield causes the current thread to move from one running state to runnable state, so that the other threads may get a chance to run. However, the next thread chosen for running might not be a different thread. So you call this function. Yeah, it's the same. Okay. So that's it. That's it for today. Next week, most probably will be a e-learning mode as well. Thank you very much. I will open a forum for you to ask the questions. So anything you can post in the forum. Thank you very much.